Here we're going to look at the equation to work out the percentage of a weak acid which is ionised. Very, very useful equation to work out percentage ionised of a weak acid at a particular pH. What we're going to do, just out of interest, is see how this equation is derived. It's not just plucked out of thin air. There is some sort of logic behind how we get to it. We start with our old friend, the Henson-Hasselbalch equation. And the first thing we do is we subtract pKa from both sides. And that would give me then pH minus pKa equals log A minus concentration over HA concentration. Now, the next thing we do is, once we've got that, is we take the inverse log of both sides. So I'm going to inverse log this. So that will give me 10 to the pH minus pKa. That equals, if I inverse log this side, I simply get rid of that log term. And that then will give me concentration of A minus over the concentration of HA. Now I'm going to rewrite this. I'm going to swap these around. I'm going to swap these two around. And if I swap those two around, log rules dictate that I need to swap those two around as well. So that then gives me 10 to the pKa minus pH. That's now equal to the concentration of HA over the concentration of A minus. What I'm now going to do is I'm going to multiply both sides by A minus. And that will give me 10 to the pKa minus pH times the concentration of A minus. And that gives me the concentration of HA. Now, the fraction of the weak acid which is ionised can be given by the following. So it's the concentration which is ionised over the total concentration of your acid, unionised plus ionised. Okay, so hopefully you can see that that is relatively straightforward. What I can now do is this HA term here can be replaced by all this, which is also equal to HA. So my fraction ionised, which I'm just going to call Fi, is there now equal to A minus concentration over all this here, which is also obviously equal to HA. So that's 10 to the power pKa minus pH times the concentration of A minus plus the concentration of A minus. Now this can be simplified and we can simplify to get rid of all these A minus terms. That simplifies to 1 over 1 plus 10 to the pKa minus pH. And remember, we want the percentage which is ionised. So if I simply multiply that by 100, that would give me a percentage. So my percentage ionised is now equal to 100 divided by 1 plus 10 to the power pKa minus pH. And that there is the equation which we had if we have a look right at the very top. If you're happy with how we got from here to here, then you can pause the video and stop the video. If you want to know how we did get from here to here, I will very briefly explain it. I think maybe some people might not have been too happy with that. Well, let's just call A minus equal to X, and let's say 10 to the pKa minus pH, all that there is equal to Y. If you look at that, what that then in effect gives me is that fraction ionised then is equal to X divided by XY plus X. Now, I can rewrite this to give me 1 over xy plus x over x. So in effect, if I flip these two round, I need to put it 1 over. It's again, put some numbers in and try it if you don't believe me. What we can do now is we can say fraction ionised is equal to 1 over xy over x plus x over x. That x cancels that x, and this here then is simply equal to 1, and therefore my fraction ionised now is 1 divided by y plus 1, which is in effect what we've got here. So that there gives you an indication of how this very useful equation, percentage of an acid, is ionised at particular pHs. Just to say that if you wanted to work out the percentage of a weak base, the method of working this out is pretty much the same. And what you get there is this would be pH and it'll be then minus the pKa.